Every steel structure is a high-energy system straining to return to its low-energy state as iron oxide. This thermodynamic drive powers a microscopic battery, where the steel acts as both the anode and the cathode. When iron atoms at the anode lose 2 electrons, they dissolve into the surrounding moisture as positive ions. These electrons travel through the metal to the cathode site, where they react with water and oxygen to form hydroxide ions. The combination of these ions creates hydrated iron 3 oxide, the flaky substance known as rust. Unlike other metals, the volume of rust is significantly larger than the original steel, creating internal stresses that can reach several thousand pounds per square inch. This expansion causes the surrounding material to crack and delaminate, exposing fresh metal to the cycle of decay and compromising structural integrity from the inside out. The rate of this electrochemical decay depends entirely on the conductivity of the electrolyte connecting the anodic and cathodic regions. Pure water is a poor conductor, but dissolved salts and atmospheric pollutants provide the ions necessary to bridge the circuit. In coastal environments, chloride ions from sea spray penetrate microscopic pores in the metal surfaces. These ions not only increase conductivity, but also actively disrupt the naturally occurring thin oxide film that otherwise slows down the corrosion process. This is why steel in industrial or marine settings degrades orders of magnitude faster than in arid regions. As the concentration of ions increases, the electrical resistance of the path drops, allowing more current to flow and accelerating the loss of metal mass. Engineers must calculate this resistance when designing the service life of bridges and residential frames located near saltliner bodies.
Nature is governed by the second law of thermodynamics, which dictates that systems move toward a state of maximum entropy and lowest energy. Refined iron is in a high-energy state compared to the iron ore found in the Earth's crust. The transformation into rust is a spontaneous process because it releases energy, measured as Gibbs free energy. For iron to remain in its metallic form, it requires a continuous input of energy or a physical barrier to block the transition. Without intervention, every steel skyscraper is essentially a temporary storage of energy that the environment is trying to reclaim. This thermodynamic instability means that corrosion prevention is not an optional maintenance task, but a fight against the fundamental laws of physics. Understanding the voltage potential between different metals allows engineers to predict which parts of a structure will fail first when exposed to environmental moisture. Localized corrosion poses a far greater threat to structural integrity than uniform surface rust because it is often invisible until total failure occurs. Pitting happens when a specific point on the steel surface becomes an anode, while the surrounding area acts as a large cathode. This creates a highly concentrated attack that drills deep into the metal, forming cavities that act as stress concentrators. A similar phenomenon occurs in crevices where oxygen cannot easily reach. These oxygen concentration cells create a potential difference between the oxygen-rich outer surface and the oxygen-starved interior of a joint. The oxygen-starved area becomes the anode and dissolves rapidly. Because these pits are small and often covered by corrosion products, they can compromise the load-bearing capacity of a steel beam without showing significant surface discoloration or thinning until the section snaps under load.
When 2 different metals come into contact in the presence of an electrolyte, a galvanic cell is formed. The metal with a lower electrochemical potential becomes the anode and corrodes, while the one with the higher potential is protected as the cathode. This principle is documented in the Galvanic series, a list that ranks metals based on their nobility. In home building, using stainless steel screws and a galvanized steel plate can lead to rapid failure if the surface area of the noble metal is large compared to the base metal. The smaller anode must provide electrons to the entire large cathode, leading to an extremely high local corrosion rate. Engineers prevent this by ensuring that dissimilar metals are electrically isolated using non-conductive washers, or by choosing metals that are close together in the series to minimize the potential difference and the resulting current flow. Hot dip galvanization utilizes the Galvanic series by intentionally coating steel with zinc. Zinc is more chemically active than iron, meaning it has a higher tendency to lose electrons. If the coating is scratched and the underlying steel is exposed, the zinc surrounding the scratch becomes the anode and sacrifices itself to protect the steel. This sacrificial protection continues as long as there is zinc remaining in the vicinity. Beyond this electrochemical defense, the zinc reacts with oxygen and carbon dioxide to form a tough layer of zinc carbonate. This layer is insoluble in water and provides a robust physical barrier that slows down the movement of oxygen and moisture to the metal surface. Unlike paint, which can be undercut by rust, the bond between zinc and steel is a metallurgical alloy that prevents the spread of corrosion even when the surface is physically damaged.
Weathering steel utilizes alloying elements like copper, chromium, and phosphorus to turn corrosion into a defense mechanism. Unlike standard carbon steel, which forms a porous and flaky rust layer that traps moisture, weathering steel develops a dense, adherent patina of iron oxyhydroxide. This patina acts as a semi-permeable membrane that significantly restricts the diffusion of oxygen and water to the underlying metal. The formation of this protective layer requires alternating cycles of wet and dry conditions. If the steel remains constantly submerged or in a very humid environment, the stable patina cannot form, and the metal will continue to corrode at a standard rate. When used correctly in bridges or building facades, this technology eliminates the need for repeated painting, relying instead on the controlled chemistry of the surface to achieve a maintenance-free lifespan of several decades without the use of external coatings. Steel reinforcement within concrete benefits from a highly alkaline environment with a potential of hydrogen level between 12 and 13. In this range, a microscopic passive film of iron oxide forms on the surface of the rebar, effectively stopping the corrosion process. However, this protection is compromised by carbonation, where atmospheric carbon dioxide reacts with the calcium hydroxide in the concrete to lower the potential of hydrogen level. Once the level drops below 9, the passive film dissolves and the steel begins to rust. The resulting expansion of the rust creates internal pressure that exceeds the tensile strength of the concrete, leading to spalling and cracking. To prevent this, engineers specify a minimum concrete cover thickness to delay the ingress of carbon dioxide and use additives to reduce the permeability of the concrete matrix, ensuring the steel remains in a high potential of hydrogen environment for the structure's entire life.
In massive infrastructure projects like buried pipelines or offshore platforms, sacrificial anodes are often insufficient. Engineers instead use impressed current cathodic protection, which involves an external power source to drive the electrochemical reaction in reverse. By connecting the negative terminal of a direct current power supply to the steel structure and the positive terminal to an inert anode, the entire structure is forced to act as a cathode. This provides a continuous flow of electrons that offsets any local anodic reactions, effectively freezing the corrosion process in its tracks. The system requires precise calibration, as overprotection can lead to hydrogen embrittlement, where hydrogen gas molecules penetrate the steel lattice and make it brittle. Monitoring stations along the structure measure the potential of the steel relative to a reference electrode to ensure the current remains within the safe window for maximum protection without compromising material properties. Modern protective coatings go beyond simple aesthetics by creating a high-resistance barrier that prevents the formation of an electrochemical cell. Epoxy coatings are widely used for their exceptional adhesion and low permeability to water and ions. These coatings work by increasing the electrical resistance of the surface to such a high degree that the corrosion current becomes negligible. Polyurethane topcoats are often applied over the epoxy to provide ultraviolet resistance, as epoxy can degrade when exposed to sunlight. In aggressive environments, a zinc-rich primer is used as the first layer to provide an extra level of sacrificial protection if the barrier is breached. The physics of adhesion is critical here, as any microscopic gap between the coating and the steel can trap moisture and initiate crevice corrosion. Advanced surface preparation through abrasive blasting is required to create a specific profile that ensures a mechanical and chemical bond.